Hi, my name is Tejaswini Atluri. For the survey research on real-time operating systems, I have taken the topic FreeRTOS. As an introduction, let me start by going over the fundamentals of the operating system, real-time operating system, and FreeRTOS. An operating system is the primary software component that facilitates the management of computer system hardware and software. An operating system is responsible for executing fundamental functions such as management of file, process, device, and memory. So it consists of four primary subsystem managers which collaborate with each other and fulfill a distinct function. The popular OS include batch OS, time sharing OS, network, mobile, and RTOS. RTOS is employed in time-sensitive contexts where the processing of data and events must adhere to strict time limits. Three types of RTOS include hard, soft, and firm RTOS. A hard RTOS is a system where its task must be completed by a given deadline. If the task is not completed on time, it could result in catastrophic events. A soft RTOS is a system where it's okay if the system tasks are not completed within the given deadline. This implies that if any given task is delayed, it should not cause system failure in most of the scenarios. In a firm RTOS, a couple of missed deadlines are valid and will not result in total failure, but missing more than a few may lead to complete or catastrophic system failures. FreeRTOS is cost-free and openly accessible RTOS developed by Real-Time Engineering Limited, designed specifically for microcontrollers and tiny microprocessors. FreeRTOS follows best practices and standards for RTOS. These standards ensure predictability and deterministic behavior in real-time and embedded systems. It includes deterministic task scheduling, priority-based preemptive scheduling, and synchronization mechanisms like semaphores and mutex. The design of system is intended to have a high level of portability, making it easy to adapt to other microcontrollers and architectures. Since it's easy to use, reliable, and compatible with many architectures and microcontrollers, FreeRTOS is widely used. History of FreeRTOS. The FreeRTOS kernel was initially created by Richard Barry in around 2003 and thereafter managed and updated by Richard's firm, Real-Time Engineering Limited. In 2017, Real-Time Engineering Limited transferred ownership of the FreeRTOS project to AWS after its remarkable success. Version 1.3.0 was released on July 31, 2018, which includes the initial version of AWS FreeRTOS. FreeRTOS is a highly popular real-time operating system that has undergone approximately 100 versions, starting with the initial version up to version 11.1.2. Goals and purpose of FreeRTOS. FreeRTOS is specifically designed and developed for deployment on extremely small embedded system. It focuses on implementing a minimalistic set of functions. FreeRTOS is developed to possess the following characteristics such as straightforward, adaptable to different systems, and is compact. FreeRTOS provides inherent support for various communication protocols which establish the connection between the devices and the cloud source with built-in security layers that safeguards the device from attacks. With the integration of AWS and FreeRTOS, it functions as a real-time operating system that offers various features for IoT devices. It is specifically engineered to operate on microcontrollers, enabling developers to seamlessly integrate devices with the cloud and construct applications for IoT. Standards and platform governing FreeRTOS. FreeRTOS follows best practices and standards for RTOS. These standards ensure predictable and deterministic behavior in real-time and embedded systems. Amazon FreeRTOS is IoT OS based on FreeRTOS and integrated with AWS IoT system. It provides the library for securely connecting devices to the cloud and simplifies IoT development. Development, debugging, and deployment of applications using FreeRTOS is compatible with various tools and IDEs such as Visual Studio Code and vendor-specific IDEs provided by microcontrollers and manufacturers. FreeRTOS offers an interface using which minimum modification could be done to run the application. Portable operating system interface allows the application to run using FreeRTOS. This enables code portability, thus making it easier for developers to work with FreeRTOS. FreeRTOS is often used with CMSIS which provides a hardware abstraction layer for Cortex and microcontrollers. This standardizes the interface between software and hardware, making FreeRTOS more portable across different microcontroller architectures. FreeRTOS design and implementation. FreeRTOS employs a solitary microkernel to manage real-time tasks. This kernel provides support for dynamic scheduling, which includes a priority-based scheduler. It also includes features for blocking and deadlock avoidance as well as ability to suspend the scheduler. A microkernel is an operating system kernel that is specifically designed to offer only the essential services necessary for an operating system to operate, such as managing memory and scheduling processes. Additional services such as device drivers and file systems are executed as processes at the user level. RTO's fundamentals includes multitasking. A typical CPU is limited to completing one operation at a time. However, a multitasking OS can create the illusion of concurrent execution by rapidly switching between activities. The image below illustrates the temporal execution pattern of three jobs. The upper diagram illustrates the apparent concurrent execution pattern, whereas the lower diagram represents the actual multitasking execution pattern. Scheduling. The scheduler of an RTOS plays a crucial role in determining the order in which tasks are executed on the processor, ensuring that all tasks are completed within the specified deadlines. FreeRTOS employs a dynamic preemptive priority-based scheduling method. This scheduler provides the user with the option to execute processes either cooperatively or using a preemptive policy. Context switching. The act of preserving the state of a paused task and restoring the state of a resumed activity is referred to as context switching. For example, a task that is halted right before carrying out an instruction moves to the state of suspension. Other tasks will be executed and have the potential to affect the value of the processor registers. After resuming, the task will be unaware of any change made to the processor registers. If it were to use the new values, the summing would yield an inaccurate result. To avoid this kind of mistake, it's crucial that when a job is resumed, its context is the same as it was before it was paused. The operating system kernel is responsible for guaranteeing this by preserving the state of the task when it's temporarily halted. Prior to execution, the operating system kernel restores the preserved context of the task when it's resumed. Coroutines. Previous iterations of FreeRTOS, specifically those preceding version 4, exclusively support the organization of a real-time program as a collection of independent tasks. Starting from FreeRTOS version 4, a real-time programming can integrate coroutines in addition to or instead of tasks. Coroutines share conceptual similarity with tasks but possess distinct basic difference. The difference includes stack utilization, scheduling, macro implementation, and limitation on usage of the RAM. Usage of queues. In a queue, items are inserted by copy rather than reference. When queuing huge things, it's more advantageous to merely queue a reference to the item. The queue usage is implemented via the blockqueue.c and polqueue.c files in the RTOS program. The queue implementation utilized by the RTOS is also accessible for application code. Tasks and coroutines can pause their execution and wait for data to be available on a queue, or for a space to become available to write the queue. Usage of semaphores. The functionality of a binary semaphore is implemented by a collection of macros. Macros utilize the queue implementation as it encompasses all the necessary functionalities without any additional code or testing burden. If necessary, the macros can be readily expanded to include counting semaphores. The semtest.c code in FreeRTOS illustrates the utilization of semaphores. Subcomponents of FreeRTOS and their functions. The subcomponents include kernel, scheduler, IPC, interrupts, timer, and the hardware interfaces. The kernel of a RTOS is defined as a scheduler. It can be understood as a program that remains active during periods of inactivity. The scheduler is a software that determines the task that should be executed and the duration for which it should run. FreeRTOS offers the option to either use a preemptive scheduler, which switches to ready state, or a round-robin based scheduler for the entire system. Inter-process communication refers to the mechanism and techniques used for communication between different processes in a computer system. FreeRTOS has support for queues, mutex, and semaphores. Interrupts. The ability to interrupt is always dependent upon the port for the individual CPU. FreeRTOS interrupt supports relies on the port designed for a particular microprocessor architecture. Timers. FreeRTOS offers a wide range of choices for programs to utilize software timers that are synchronized with the hardware. The hardware interface. It encompasses the memory, memory management, and various network interfaces. Complexity and cost of implementation. FreeRTOS is completely free to use with no associated fees. FreeRTOS is distributed under the MIT open source license, which is permissive license that imposes minimal restriction on the use of the software. You can bring a product to the market utilizing FreeRTOS without the need for any communication or financial obligation with the FreeRTOS organization. It is very scalable, uncomplicated, and user-friendly. FreeRTOS provides a more compact and simple option for real-time processing in cases where other complex operating systems are unavailable. Requires a minimal amount of ROM, RAM, and processing requirements. RTOS kernel binary image usually ranges from 6K to 12K bytes in size. The core of RTOS is comprised of just 3 C files, making it highly straightforward. Pros and cons of FreeRTOS. The pros includes that the FreeRTOS is an open source operating system, which means that its source code is accessible to the public without any cost. It's easy to use, it has great security, it's scalable and adaptable. The cons include that it's difficult to implement complex real-time system with many tasks. It requires third-party support, it has feature restriction, it has compatibility issues, and we require prior knowledge. Companies which are currently involved in this line of business. A lot of vendors are collaborating and are partners with FreeRTOS. Top manufacturing companies using FreeRTOS include Actron Air, Advanced Navigations, etc. Electrical and electronic companies include Philips. The RTOS market worldwide is anticipated to rise at a great rate between 2023 and 2031. The main segments of FreeRTOS clients by industries are information technologies and services, about 16%, and semiconductors, about 13%. Most FreeRTOS clients, are 58%, are located in United States. The majority, that is 50% of the customers utilizing Amazon FreeRTOS, are classified as large, with a revenue exceeding $1,000 million. Additionally, 31% of customers are categorized as small, with a revenue below $50 million. Future trends of FreeRTOS. The future of FreeRTOS looks promising. It's widely used in varied industries and is one of the most popular RTOs. There is a discussion forum on FreeRTOS website wherein users can contribute and help develop new features or address the bugs that exist. This is one of the most reliable way where the product is developed and enhanced periodically. The latest version of FreeRTOS kernel is version 11, which was released a few days back on April 22nd, 2024. This release incorporates the subsequent functionality such as symmetric multiprocessing, security is improved, the tracing tools are improved, and various improvement and optimization have been made to prevent buffer overflow and strengthening the heap. Conclusion. FreeRTOS is a promising RTOS which can be used for embedded devices. It supports various features and more development of additional features are planned for future. With the proliferation of the IoT devices, autonomous system and other applications requiring real-time capabilities, there is an increasing demand for reliable real-time operating systems like FreeRTOS. FreeRTOS is not limited to traditional embedded system but is also expanding into areas like robotics, industrial automation, and automotive applications, further broadening its relevance and impact. Overall, FreeRTOS is poised to remain a significant player in the real-time operating system landscape, continuously evolving to meet the need of diverse embedded and IoT applications. These are the various references using which the project was completed. Thank you.